Today I'm going to talk about performance evaluation of silane in concrete bridge decks using transmission X-ray microscopy. So let's review some background about the durability and the issues that we can see in concrete structures. Durability of concrete is defined as resistant to internal and external deterioration influences. And as it can be seen, and it has been shown, that the majority of the structures fail because of the lack in durability performance, not strength performance. And the most important deterioration factor is moisture, because moisture itself or having chemicals dissolve into the moisture and penetrating into concrete can damage the concrete. And in terms of corrosion, when steel reinforcement is exposed to moisture and oxygen, it can create rust. And these rusts occupy more volume than the original steel and cause internal pressure and cause cracking and delamination and pops of the concrete. And these are some examples of the exposed reinforcement, because the top layer or the cover of the concrete is delaminated because of those internal pressures induced by the rust products. What is the solution to remove or prevent corrosion in our structures? We can do many things during the construction. For example, during the mix design of the concrete, we can use SCMs and we can develop a good mix design that is low permeable. We can use non-corrosion rebars, or we can use corrosion inhibitors in our mix design, or during the construction we can use cathodic protection, or we can use some anode sacrifice. But when it comes to the existing structures, we don't have too many options. One of the options is cathodic protection, and the other one is applying sealers. The goal of applying sealers, is to keep moisture and oxygen out of the concrete and prevent them from reaching to the reinforcement level. These sealers can create a hydrophobic layer on top of the concrete. So by doing this, we prevent the moisture just penetrating into concrete. One of the sealers that we typically use in bridge structures is silane. Silane chemically react with the cement paste just to form a hydrophobic layer on top of the concrete, and opposed to epoxy coatings, it doesn't create any visible coating. It's something transparent, but it penetrates a few millimeters down into the concrete, and then by repelling the water, it has been shown that is an effective approach for reducing the external fluid into the concrete. However, it has been shown that the results by using silane is different. We could see different performances, and one reason is that there is not any standardized test method just to evaluate those silane or those coatings. In 2018, Oklahoma DOT reached out to us, and they asked that during one of the evaluation, they found that the silane performance between different bridges that applied by different contractors showed different performances, and they didn't know why. They reached out to us just to do the analysis and understand what happened in those silane applications and what is the reason for different silane performances. So for doing this, we visited 14 bridges. We took one core from each bridge. Each core was 4-inch diameter, and the concretes that we took core from, they had water to cementitious ratio between 0.41 to 0.44. Half of the 14 cores that we got, 7 cores, they had 20% Class C fly ash in them, and the other half, they were plain concrete. When we transferred the cores into our lab, the first thing that we did, we polished 9 spots. We polished 9 spots on top of the surface, and then we measured the silane penetration into those samples. So it means for each core, we had 45 measurements. So The silane penetration depends on many factors. For example, the surface tension of the silane itself, or the viscosity of the sealer, or the concrete properties, the porosity, everything can impact the silane penetration. For all 14 cores, we measured 45 measurements of the silane penetration. And as you can see, the first observation is that we have high variation in the penetration of the silane, right? So it means that the silane didn't penetrate uniformly. And then when we compare the silane penetration with the required penetration depth that is asked by many specifications, the average value didn't reach to the required penetration depths. Now the question is that, is the silane still effective in reducing the moisture ingress into concrete or no? And then how evaluate the effectiveness of the silane, because there is no any standard test method. To do that, we decided to use TXM method. What is TXM? In TXM, we put the concrete sample between X-ray source and a detector. Then X-ray shoot the X-ray beam to the sample. Some of the X-ray absorbed by the sample, and some pass through the sample, reach to the detector. And then, similar to the X-ray images or radiograph images that you can get in a doctor, you can see the high density parts have darker gray values, and those that have soft or low density, you can see that they appears as brighter colors. The same thing happened in the concrete. For the aggregate that we have a denser material, you can see this darker. For the paste is a little bit lighter. And then if we have airways, it should be pure white or close to the white, right? So by doing this, we took one initial image from the core that we got. And then we applied a type of tracer solution. The tracer solution that we used was Ki, potassium iodide. And then we took images from the same concrete, from the same direction over time. And as you can see, by having the tracer solution on top and penetrating into the sample, 7-day image, you can see is a little bit darker than the initial image. 14 days is darker than even 7 days and initial. And 20 days is darker than all of these, right? So when we subtract the images from different ages or different days of ponding from the initial image, you can see the penetration of the iodine into the sample. And then by having some calibration samples, we can convert the Gray values of the sample to the concentration of the iodide, right? Why we choose iodide, I can talk about it later. But when we have the concentration values attributed to each Gray value in this sample, we can get the concentration profile. When we have concentration profile, and by using the fixed second law, we can calculate the diffusion coefficient. Diffusion coefficient is the most important parameters when we want to deal with the service life of the concrete, right? And then by reaching to the zero concentration, we can see how much chloride or how much iodine has been penetrated into the sample. So by using this technique, we can get 3 different information: the surface concentration, the slope, that means the diffusion coefficient, and then when it reached to the zero concentration, that means the penetration depths of the detrimental chemicals. The reason that we use Ki solution or potassium iodide is that you can see 2 different samples. One sample is ponded with water on top, the other one is ponded with Ki. As you can see, water cannot be detected by X-ray, but potassium iodide can be detected. This is the reason that we use potassium iodide, because when it penetrates into the sample and by taking multiple images, we can see how far it has been penetrated. And the other reason is that for potassium iodide, it has not almost the same, but very close molecular size to the sodium chloride. To summarize, the technique that we use for this type of forensic investigation was that we put the sample between X-ray and detector. We took radiographs at different times after ponding. Then by having a MATLAB code, I align all of those images just to project all images at different times on the initial image to be able to subtract and get the images similar to this. Easily we can see the penetration depths, and then by having that and using the calibration curves, we can come up with the concentration profiles. For this study, for the cores that we received, we took 2 miniature cores from the top where we have the silane material, and we took 2 cores from the side, so we don't have any silane in this side, right? So these 2 cores are named as no silane treatment, and those 2 cores are representing the silane-treated samples. Then we use a hydrophobic wax to seal around the samples, as you can see here, and then we put the samples in different cells. These cells are sealed, and then there is no any leakage or there is no any ion exchange between these cells, and then we fill these cells with potassium iodide, and then by having these sealers around the sample, we are pretty sure that we have one directional penetration into the samples. There is no any penetration from the sides. And when we measure the penetration depths, everything is penetrated only from the surface. These are examples of the results of the concentration profiles obtained for the samples treated with silane, shown in solid black, and those samples that are took from the side without any silane. As you can see, even by having less penetration silane into the samples, less than the required penetration depths, still you can see the concentration of the iodine is less than concentration of the iodine in the samples that are not treated with silane, right? So it means that still silane was effective. But I just sorted all the samples, our 14 samples, from the minimum concentration of the iodine to the maximum concentration of the iodine for those samples that are not treated with iodine, and those samples that are treated with iodine. So you can see for non-treated samples, still we have higher concentration of iodine compared to the samples that are treated with silane, right? It definitely shows that the silane was effective in reducing the penetration of the iodine or other detrimental chemicals into the sample. Look at the average value of the penetration depths or the penetration depths of the silane, the iodine is 2.7. And for the samples that are treated with the silane is 0.3. As you can see, 9 times higher. We had 9 times higher penetration in non-treated samples. Let's look at this sample, sample 6, that as you can see, remember in the previous slides that I showed, it had the highest variation. It has the highest variation, and as you can see, because of that highest variation, the difference between treated and non-treated was minimum, right? But look at the other sample that it had the minimum variation. Although it had the minimum average value of penetration, but it had the minimum variation. And as you can see, the treated samples perform much, much better than untreated samples. However, in some samples, we observed something interesting. We found that up to 2 millimeters, we have pretty low concentration of iodine. But after 2 millimeters, we started to see increase in the concentration of the iodine. It means that for some reason, iodine bypassed the silane. And then when it bypassed the silane, it increased the concentration of the iodine, reached to the same amount of the untreated samples. To investigate why it has happened, we use computed tomography or a micro CT scan. In this technique, again, we put the sample between X-ray and a detector, but this time, images are captured at different angles. And then when the images are taken at different angles, we can see different cross-sections. So in this project, we got more than 1,000 cross-sections. And then by projecting all of these cross-sections and then creating a 3D image that we call it reconstructing the 2 images to 3D image, we can analyze the sample for many things, like the air void, the the crack detection, anything that we want to see. In this case, after evaluating those samples that had higher iodine penetration after 2 millimeters, we could see there is a crack. In this case, you can see there is a crack on the aggregate, right? So it means that this crack provided a path for the iodine just to penetrate into the sample. So we figured out that the cracks can compromise the effectiveness of the silane or and the other sealer materials. So we conclude that silane penetration for this specific project for Oklahoma penetrated below the specification limits. But despite this, it showed that the samples, the treated samples, still had 9 times less penetration of the chemical ions into the sample. And then we found that the surface cracks allowed chemicals to bypass the coating and reach to the deeper part of the concrete. So it means that the different performance of the silane that observed between different contractors didn't come from the contractor performance. It came from the cracks that had happened after they applied the silane material. So this is the reason that after a while we need to reapply the silane, and the best method is to apply the silane after we are sure that the concrete, the newly constructed concrete, has developed all of its crack that we expect to see all of those cracks in 1 year or 1.5 years. So the best method is to wait until 1 year, 1.5 years, and then apply these materials to the concrete just to make sure no new cracks is happening and it's not going to bypass the silane material. We have published one paper from this research that we have done. You can find by scanning this QR code here, or if the QR code didn't work for you, you can search this title, and then you can find this, and this is an open access paper. You can have easily access to this paper. One thing that I wanted to note here, the technique that we used was TXM, which is a very expensive technique, and we can use it in the lab, not in the field, right? But according to this technique, we developed another technique that if you search the literature for using dental X-ray scanning, or CHIP, C-H-I-P, you can see the other technique that I developed during my PhD work to use instead of this technique that is pretty expensive. By CHIP, or dental X-ray scanning, we can get with the same results. So if you search in the literature, you can find a paper that I published on that, testing exactly the same samples, and you can compare the results from TXM and dental X-ray scanning that cost maybe just $30K just to come up with that test setup in your lab if you want. That's it. I'm ready to take any questions.